All right, it is now time to move on to chapter 3. Chapter 3 is all about methods of integration. So, basically speaking, how do I find the antiderivative of stuff that's hard, is what it is. So, just like we had derivative rules in Calculus 1, these are going to be antiderivative rules to go backwards. Okay. The first one is going to be the opposite of the product rule. So remember, the product rule said this. If I was going to take the derivative of something, let's just say u times a v, okay? The derivative of u times v. What we said this was, you would take the derivative of u and then multiply that by v. Plus, leave the u times the derivative of the v. So now what I want to learn is how do I go backwards from that, okay? So imagine I did that. So I'm going to take the integral of this, integral of this, integral of this. Integral of a derivative, they cancel out, so this is just u times v. This would just leave me with u, but I'm stuck with a dv, plus this would just leave me with a v and leave me with a du. This is where they get this rule called the integration by parts rule, which is just the reverse product rule, okay? This is where, because what I can now do is I can move this term over there, and I get that the integral of this, the integral of u times dv is equal to, again, because I'm just moving this term over there, u times v minus the integral of v du. There it is. That's where I get this from. So if I see a product inside of here, I can use this rule. Again, this is the reverse power rule that I use whenever I see a product. So let's look at an example. The first example is going to give us what I want to use, okay? Use integration by parts with the u being equal to x and the dv being equal to sine of x dx to evaluate integral of x sine of x dx. Look at that. Number one, integral of x sine of x dx. Now, how I know I want to use this is because there's a product. X times sine of x. That's a product, right? So I'm going to use this, which I said is the reverse product rule. Now, what we have done in the past is we'd say, oh, well, let's find a u so that I have a du, right? Well, if you notice, that doesn't really work here, because if I tried and let the u be equal to an x, du would just be dx, and it wouldn't change anything, right? If I tried to let u be equal to sine of x, du would then be cosine of x, which I don't have, right? So it doesn't work. What I have been trying up until now wouldn't work here. Once again, I have a product, so I'm going to use this rule here. This problem even goes so far as to tell us what I want to use for the u and for the dv. It says let the u be equal to an x and let the dv be equal to sine of x. So u equals x and dv is going to be sine of x dx. So from there, what I still need is the du for this part, and I need the v for the v, which appears here and there. So for the du, I'm just going to take the derivative of the u. The derivative of the 1x is just 1 dx. Not hard. To get the v from the dv, if I know what dv is, to go backwards and get v, I need the antiderivative. The antiderivative of sine of x is negative cosine of x. So that's my v. So now that I have everything I need, I can put this into the formula that I have there. So it starts with uv. So I'm going to do u times v, which will give me negative x, cosine of x, minus integral v du. So the v is negative cosine of x, which would make this plus cosine of x. Du is just dx. And I like this because now I can evaluate this part right there. So this is going to be equal to, the first part is good, nothing I need to change there. The antiderivative of cosine is sine. And as always, don't forget plus c. So this is how I handle it when there's a product. Example number 2 is kind of the same. They want us to evaluate integral of x e to the 2x dx, but once again, they tell us what I want to use. So I'm going to let u be equal to the x, and I'm going to let dv be equal to e to the 2x dx. Let's think about why I want to do that. Oh, sorry, u, not du. It said let u be equal to x and dv be equal to e to the 2x dx. So remember, the idea is that I want it to get smaller, right? I want to turn it into something that's not hard, right? Something without a product. If I let x be the dv instead, to find v, I would have gotten x squared divided by 2, which would have left x squared in this slot right here. So then I would have had another product here, which meant I would have had to then do this again and again and again and again. And the idea is I want this to get smaller with fewer terms there, right? I don't want a product there. So like over here, right here, I want to basically get rid of the x right here. And I can let that be the u, because then du is just a 1. So then I no longer have a product there. So that's why. So the idea is I want it to where I eventually don't have a product. Okay. All right, so if dv is equal to e to the 2x, we know the antiderivative of e is just e. Anti, right? So I'm going to go backwards. If I took the derivative of this, I would have had to, by the chain rule, I would have then brought down a 2. Since I don't have a 2 here, I've got to make it 1/2. Because then when I brought down a 2, 2 times a half is equal to a 1, which is what I have there. So now using this, it starts with uv. U times v would be 1/2 x e to the 2x minus the integral v du. So v has a 1/2, so I'm just going to bring it out front. E to the 2x dx. So then do it again. And this one isn't hard because I no longer have a product there. So now I can just do that outright. First term stays the same, minus 1/2. The antiderivative of e to the 2x, as we just said over here, is 1/2 e to the 2x plus c. 1/2 times 1/2 is 1/4. So I get 1/2 x e to the 2x minus 1/4 e to the 2x plus c. As I say a bunch of times, and as I will say a bunch more times, if any of that does not make sense, please let me know. So starting here at example number 3, they stop telling us what u and dv are. So now I'm going to have to figure it out for myself. Natural log of x over x to the third dx. So again, the idea is I no longer want a product there. First things first, this doesn't look like a product, it looks like a quotient. But remember, when there is a power on the bottom, I can bring it up top by making my power negative. So that's the same thing as this. So product rule. Okay. So again, I don't want a product there. So to follow suit with what I have done, you would at first think, okay, let's let u be equal to x to the negative third, because that seems to be what I have done. But the du would have to be negative 3x to the negative 2 dx. Let's see if that works. If the u is equal to x to the negative third, my dv would have to be the natural log of x dx. So think about this though. I would then need this to get the v. Can I take the antiderivative of the natural log of x? The answer is no. So it does not make sense for the natural log to be dv, again, because I cannot take the antiderivative of that. So this wouldn't work here. I'm going to have to switch them. And u would have to be the natural log of x, because I can take the derivative. The derivative of the natural log of x is 1 over x. Easy enough. Which means my dv would have to be x to the negative 3. Take the antiderivative of that. Add 1 to the power would make it x to the negative 2. Divide by my new power would give me negative 1/2 x to the negative 2. So uv would be negative 1/2 x to the negative 2, natural log of x, minus integral v du. I can bring the negative 1/2 out front, which would make it plus 1/2. X to the negative 2 times 1 over x, which is x to the negative 1 dx. But look at that. That's really nice. Even though it's a product, I can simplify it. X to the negative 2 times x to the negative 1 is x to the negative third. So when I take the antiderivative of it, I just have to add 1 to the power, which would make it negative 2. Divide by that new power would make this negative 1/4 x to the negative 2. And of course, always put plus c. So again, I have to be able to take the antiderivative of dv, which is why I couldn't let dv be the natural log of x, because I cannot take the antiderivative. Let's do another example. This one's actually a little bit easier than this one we just did. Example number 4 is the integral of x ln of x dx. So same thing here. My first gut thing would be, oh, well, obviously, let's let u be equal to x, because then du would just be equal to dx, so that's really nice. But that would mean dv would have to be the natural log of x, which I cannot do because I can't take the antiderivative of that to get the v. So instead, u has to be the natural log of x, which would make du 1 over x dx. Therefore, dv is going to be x. Take the antiderivative of that, x to the negative 2 over 2, which is 1/2 x squared. So now work this out. uv would give me 1/2 x squared natural log of x minus the integral v du would give me 1/2 x squared times 1 over x dx. Well, that's really nice because x squared times 1 over x is just x. So this is 1/2 x squared ln of x minus 1/2 integral. Once again, x squared times 1 over x is just x. So then take the antiderivative of that. Let's first term stays the same, would give me x squared over 2, which is negative 1/4 x squared plus c. As I've always said, if that doesn't make sense, let me know. Example number 5. Let's do the integral of x squared e to the 3x dx. So for this one, again, I want to find a u and a dv. Luckily here, I can take the antiderivative of either one of those. So that's so then that's good. So then what I really want is a u so that the derivative is going to bring it down, right? Because the whole idea is I want to make it to where there's not a product, right? So it would make sense now to let u be equal to x squared, because every time I take the derivative of that, my power is going to go down. So eventually I won't have a product there. So let's let u be equal to x squared. Du would be 2x dx then. So the dv would have to be the e to the 3x part. Antiderivative of that, since my power is 3x, when I take the derivative of that, it would give me a 3. So I need to make sure to put 1/3 e to the 3x. So starts with uv. U times v would be 1/3 x squared e to the 3x minus the integral v du. Have a 1/3 here and a 2 there, so this is going to be 2/3 out front. X e to the 3x dx. Now, why is this one kind of weird? Because now I have another product here, so I've got to do this again. Again, because there's another product here. So I've got to do it again. So if it helps, let's name these U1 and V1 so that I can now do U2 and V2 because I've got to do it one more time. So U2, once again, I'm going to let that be the x because when I take the derivative of that, it's just a 1, so there's no longer a product there. That's going to be 1 dx, which would make v2 dv2 e to the 3x dx, which again would make v2 if you take the derivative of that, 1/3 e to the 3x. So let's do this again. This first term doesn't change. Minus 2/3. This whole thing is now uv, which would give me 1/3 x e to the 3x minus the integral v du. There's a 1/3 out front, so put the 1/3 e to the 3x dx. Let's simplify this. 1/3 x squared e to the 3x. 2/3 times 1/3 is 2/9, so minus 2/9 x e to the 3x. Minus 2/3 times minus 1/3 is plus 1/9 integral of e to the 3x dx. And the antiderivative of e to the 3x, as we've already seen, is 1/3 e to the 3x. So this last term, I would get a 1/3 here, which would make that 1/27. Ooh, 2/3 should have been 2/9. So 2/27 e to the 3x plus c. So the only change here is that since whenever I do this once, I still have a product there, do it again. So there are going to be times to where I've got to do this rule more than one time. For those of y'all who are taking my Cal 2 class at CCC, example number 6, I'm actually going to omit that one. The reason is because this has e to the t squared, so actually you can't take the antiderivative of that. So that's why. So omit example number 6. Let's move on to example number 7. This one's a lot of fun. For me, I think it's a lot of fun. If you like math, it's a lot of fun. Which if you're taking Cal 2, then you probably like math, at least a little bit. All right, integral sine of the natural log of x dx. This is example number 7 for those of y'all working on the handout. Okay, so At first glance, many people see this and think this is sine times the natural log of x. But that's not how sine works, right? This is sine of the natural log of x. So taking the antiderivative of this, we don't even know where to start, right? Because this is sine of the natural log. Initially, you may think, let's try u substitution, right? But if I did u substitution, u would have to be the natural log of x, so du would have to be 1 over x. 1 over x, that's not here, so that doesn't work, right? And then integration by parts, initially you may think, well, that doesn't make sense because that's not a product, right? But remember, everything is a product with a 1. So I could say this is like 1 times that. That kind of makes sense? So let's figure out what the u and the dv are. Well, the entire point is I can't take the antiderivative of this, right? So it doesn't make sense for the dv to be sine of the natural log of x because I can't do that because that's the reason I'm doing this, right? So let's let that be u because I can take the derivative. So let's let sine u be equal to sine ln of x. I can take the derivative of that, do the outermost part to start with. The derivative of sine is cosine. By the chain rule, multiply that by the derivative of the natural log of x, which is 1 over x dx. So dv would have to be this 1. Antiderivative of 1 is x. So uv would give me x sine natural log of x minus the integral v du. X times 1 divided by x, they cancel out. So I'm left with just cosine of the natural log of x dx. Well, once again, antiderivative of this, can't do it, right? So I'm going to do it again. I'm going to do by parts again. Once again, this is like saying times a 1. So pretend there is a 1 out front. So again, I can take the derivative, so let's let that be u. So du would be, the outermost part is where I'm going to start. The derivative of cosine is net negative sine. The derivative of the natural log is 1 over x. Therefore, dv is going to be the 1 that's out front. So v has to be x. So this is going to be equal to, first part doesn't change, minus uv would give me x cosine natural log of x minus the integral v du. Once again, x times 1 over x, they cancel out. So I'm left with just negative. I'm just going to make this plus sine ln x dx. Simplify this a little bit. We end up with x sine of natural log of x minus x cosine natural log of x minus the integral sine ln x dx. But notice then, what's really weird about this is I end up with the same thing I had to start with. So what's going to happen then is I'm going to just get stuck in a loop, right? I'll just keep doing it over and over and over and over and over again. So what I can actually do now, instead of doing that, instead of just being caught in like a weird time loop, right? I can turn this into an equation. What I want is the antiderivative of sine of, I almost messed up there, sine of the natural log of x. I have one of those over here. I have one of those over here. Let's put those on the same side and I can solve it. So if I were to add this to this side over there, I would end up with 2 integral of sine ln x dx is equal to x sine ln x minus x cosine ln of x. So to solve for the part I want, I just have to divide this by 2. So the integral of sine ln x dx is equal to 1/2 of this. So you could write that as just x sine ln of x minus x cosine ln of x over 2. So if it's looking like you are going to get stuck in some kind of loop, you can do this instead. Treat it like an equation. Bring this over there and divide it by 2. Let's do another example. Example number 8. Integral of x squared sine of x dx. Have a product here. Again, the idea is I want to break it down to where I no longer have a product. So I'm going to let u be equal to x squared, because then my power is going to be decreasing, which is good. Du would then be 2x dx, which would leave dv to be sine of x dx. The antiderivative of sine of x is negative cosine of x. So this becomes uv negative x squared cosine of x minus the integral v du. So the minus sign makes it a plus. I have a 2 out front, so just put a 2. X cosine x dx. I still have a product, which means I've got to do it again. This time u is going to be the x, once again, because when I take the derivative of that, it's going to bring my power down to just a 1, so that's good, which would leave dv to be cosine of x. Antiderivative of cosine is sine. So this becomes negative x squared cosine of x plus 2 times uv, so x sine of x, minus the integral v du. Simplify this, negative x squared cosine of x plus 2x sine of x. Antiderivative of sine is negative cosine, which would make this plus cosine. So plus 2 cosine x dx, or not dx, plus c. Like that. So once again, I let the u be equal to x squared because my power would eventually go down to where I don't have a product, like I didn't there. Let's put some bounds on here and make these definite integrals. Example number 9. We're going to do the integral from 0 to pi over 2 of x cosine x dx. Now, since I have a product here, obviously I'm going to be having to do the whole like u dv thing. So it helps to ignore the bounds until the very end. Okay, so for now, just ignore them, pretend like they're not even there. Okay. So once again, this is a product, which means I've got to do it by parts. I'm going to let u be the x because it's going to break it down to where I no longer have a product. So du would just be dx. dv would then have to be cosine. Antiderivative of cosine is sine. So this is going to be uv x sine of x minus the integral v du. Antiderivative of sine is negative cosine. The negative is going to make it positive. So this is going to be x sine of x plus cosine of x. And we're going to do that. Like I said, now that I'm at the very end, I can go ahead and put my bounds there. So as always, do my top bound first. So it's going to be pi over 2 sine of pi over 2 plus cosine of pi over 2 minus, plug the 0 in, 0 sine of 0 minus cosine of 0. Sine of pi over 2 is a 1. 1 times pi over 2 is pi over 2. Cosine of pi over 2 is 0, so that term's gone. 0 here, so that's going to be 0. Cosine of 0 is 1, so minus 1. Again, ignore my bounds until the very end, then I can put them there. The notation notation just gets a little weird if I try to like put there, because then technically I would have to write it like this: 0 to pi over 2 with bounds, 0 to pi over 2 here. That's just a lot. So instead, just pretend like they're not even there till the very end. Then worry about it. Example number 10 is going to take what we learned in chapter 2 and apply it here. Find the area of the region bounded above by the graph of y equals inverse tangent of x and below by the x from 0 to 1. So remember, this is the first thing we did in this class. This is going to be integral from my bounds, which is 0 to 1, of my function inverse tangent of x dx. So think about this. Can I take the antiderivative of inverse tangent of x? The answer there is no. We can't. There's no rule there. But I can take the derivative. So I'm going to do like what I did before and treat this as if it's times 1, because it kind of is, right? I can take the derivative, so let u be equal to the inverse tangent. The derivative of that from Cal 1, we know the derivative of that is 1 over 1 plus x squared, which would mean the dv would have to be the 1, so v is x. So this is going to become uv x inverse tangent of x minus the integral v du. It's over 1 plus x squared dx is what I end up with there. So to solve this, I'm going to need u substitution. We're going to let u be equal to the 1 plus x squared, because then du would just be 2x dx. I have the x, which means I just need a 2. Put a 2 there, put a 1/2 out there. That's x inverse tangent of x minus 1/2 integral. This would just become 1 over u du, which I know is going to be the natural log of the absolute value of u. So x inverse tangent of x minus 1/2 natural log absolute value of the u, and we already said u was 1 plus x squared. And I'm doing that from 0 to 1. So plug in a 1 first. 1 inverse tangent of 1 minus 1/2 natural log 1 plus 1 squared, minus, plug in the 0, 0 times inverse tangent of 0, minus makes it plus 1/2 natural log 1 plus 0 squared. Work this out. 1 is just 1. Inverse tangent of 1, if you look at the unit circle, is pi over 4. 1 squared is 1. 1 plus 1 is 2. So this is 1/2 times the natural log of 2. 0 makes this whole term 0. 0 squared is 0. 1 plus 0 is 1. The natural log of 1 is 0. So this whole term is gone too. So I get pi over 4 minus 1/2 natural log of 2. Once again, as I've said a billion times, we are using everything we have learned in Cal 1 and Cal 2 and brought it all into like one place. So if anything doesn't make sense, let me know. It may also be helpful to like go back and review my lectures from Cal 1. That may be helpful. One more example from this section. Again, it's applying stuff from chapter 2 and bringing it forth here. Example number 11. Find the volume of the solid obtained by revolving the region bounded by the graph of f of x equals e to the negative x, the x-axis and the y-axis, and the line x equals 1. I'm going to rotate that around the y. So it is a function in terms of the x rotated around the y, which means I want to use the shell method, right? Remember, the shell method said the volume is going to be equal to 2 pi integral from a to b of x f of x dx. So we're going to do that. 2 pi integral, since it's going from the x to x is equal to a 1, my bounds are going to be 0 to 1. X times my function, which is e to the negative x, dx. So this is a product, which means I've got to do it by parts. So I'm going to let u be equal to the x again because I want to try to break it down, right? So if u is x, du would be 1 dx. So the dv has to be e to the negative x. The antiderivative of e to the negative x is negative e to the negative x, because that's what I would need for the derivative to be that, right? Because I would bring down the minus sign to make it positive. So 2 pi times this whole thing, u times v would give me negative x e to the negative x minus the integral v du would make that plus e to the negative x dx. As I just said, the antiderivative of negative, or e to the negative x is just negative e to the negative x. So that's what I end up with from 0 to 1. This equal sign should have been here. I was like, why does that look weird? There we go. And then it goes down. Sorry about that. So let's work this out. 2 pi, plug in the 1 first. Negative 1 e to the negative 1 minus e to the negative 1 minus, plug in the 0, which make it plus 0 e to the negative 0 minus makes it plus e to the negative 0. So negative e to the negative 1 minus e to the negative 1 makes it minus 2 e to the negative 1. That would make that 0 right here. E to the 0 is just 1. I'm okay if you stop right here. Technically, though, I could multiply by the 2 pi. So negative 4 pi e to the negative 1 plus 2 pi. And here we go. So once again, I have just taken everything we have done in Calculus 1 and so far in Cal 2 and just joined it all up. If something doesn't make sense, please let me know. I will be happy to help you out.